Okay, let's continue our journey into electrostatics. Um, so let's talk about electric fields now. Come on, now, electric fields. And when we say fields, what exactly do we mean in physics when we talk about a field, a gravitational field or an electric field? What does that mean? So um, you often hear in movies and so on a force field, and that's exactly what we're talking about. So a force field, it is some area where something feels a force, okay? And I'll just remind you before we move on here, because there are some parallels, that with a gravitational field, if you have a mass, around that mass will exist a gravitational force field represented by arrows. And how these arrows are drawn is you imagine that you take a test mass, since gravitational fields act on mass, and you move it around in space, and you see in which direction a force is acting on this object, right? So you can feel, if this were the Earth, the weight of the object anywhere you place it around the Earth, okay? So that therefore we can draw a force field that looks like this. Now gravitation is always attractive, all right? Whereas electricity is not always attractive. So the first thing we need to talk about is how we're going to define an electric field, right? It's sort of easy with a gravitational field, just move the mass around, you know what's going to happen. It's a little more tricky with charge because we're dealing with two types of charge, right? So that's the first thing we just need to remind ourselves. There are two types of charge, and how they behave is a little bit different. There's positive, and there's negative. And positives and negatives pull together, but positives and positives, or negatives and negatives, they repel apart, okay? So what we'll do here is let's draw a positive charge. So imagine this is something, you know, some sort of sphere that has had electrons removed from it. So the balance of charge has changed, okay? Where the negative charge went, we've taken it away. It's out of the picture right now. We just have an object with positive charge sitting there. It's perfectly fine. This can be done, okay? So how we test the electric field is we take a test charge, much like we took a test mass, and that test charge is always going to be a positive test charge, right? So if you imagine we put a positive test charge anywhere around here, what type of force would it experience? Would it be attractive? Right, it would be repulsive. So then you can go around and you can say, okay, so for a positive charge, the field will always point away from that, or outward, okay? Why? Because the field itself is based on the force experienced by the test charge. So it becomes pretty straightforward to figure out what's going to happen with negative. Okay, so if we take our positive test charge and we move it around the space here in the force field around this negative charge, you will always have an attractive force. So that's the first thing to think about when we're talking about fields, okay? Electric fields, I should say. Out of positive, you don't have to memorize that because just remember the test charge is always positive, and in to negative. Why is it this way? It's convention. There's nothing special really, you know, about choosing a positive test charge. It was just done sometime, you know, historically, and that's the convention we go by. You can also probably imagine, just separate this out so we know that these are like meant to be like sort of all by themselves. But what would happen, or what sort of field would you expect if you were to place two oppositely charged objects nearby? So now imagine we're plopping the test charge all around here and mapping which way the force points. If we put it right in the middle, well, attracted to the negative and repelled from the positive, it's pretty straightforward that you would get something like that, okay? And if you were to move it up or down anywhere along this line, okay, exactly in the middle, okay, the forces would sum, right? Essentially what we're saying is we're going to add these fields together. So out of this plus into that, together, the sum of those forces, right? So we just imagine, put over here, let's say we're right at this spot. You have this, right, out of the positive, plus this, into the negative, right? The net effect of that is this. So anywhere along this line, you have a directly rightward facing force, right, on this test charge. If you move closer to the negative, right, we'll talk soon about, I mean, fields all work under an inverse square law, right? So the closer you get to the negative, the more it takes over. So what that ends up doing is you end up with this kind of like, you know, shape like this. And this becomes logical if you think about the force that your positive test charge would be experiencing, depending where it is between these fields. So you get this kind of a thing, right? Yeah, you can think of it that way, right? You know, the way that I found it sort of easiest to think about would be imagine like there's like a wind blowing out of a positive, right? And, you know, sucking into a negative. If you think about that, right? And the wind is blowing more strongly the closer you are, all right? So as this wind blows away, it's going to start to be affected by the sucking in of the negative, and it's going to kind of bend around. You can almost think of, I think it was maybe Michael Faraday who said, these are almost like how act like little sails in the wind, right? Depending where they are, they feel a force based on the strength of the wind and the direction of the wind, just like a sailing ship would. So that often helps me to work out what these would look like. And I mean, really, I don't think it's too difficult to kind of understand sort of what they would be like. So now if we put two positives nearby each other, imagine they both have winds blowing out, right in the middle, you would actually experience a null point, right? Point where those fields, or those winds, and we're assuming, right, that these are the same size of charge right now. If you increase the size of the charge, then the wind, if you want, blowing out of one becomes larger, right? So you get more field lines coming out of it. And some sort of interesting things happen. Like, for instance, this line would kind of push more towards the negative if we added more charge to the positive than to the negative, and so on. But I mean, I don't think we have to get too wound up with all of that. So these would blow out towards each other. They'd essentially interfere, and you get this kind of a scenario happening. Okay, we're right in the middle. In the middle, you get like a blank spot. And I'm not going to draw it, but if these happen to be negative charges, all you would do is flip the direction of the arrows, okay? And it would be the exact same thing. These, by the way, if you've ever played around with magnets and iron filings, you'll get a pattern that's a lot like this. You know, although instead of negative and positive, you have north and south. You know, if you put two north poles together or two south poles together and you drop the iron filings, they'll kind of fall into these patterns and they sort of line themselves up with the field lines. Sort of something neat to check out. Maybe I'll grab a picture of that. All right, so I just grabbed a little picture off the net of some iron filings. This is north and south. But you can imagine this is positive and negative. If this were positive and this were negative, you can imagine your field lines would, let's just change it over actually. Kind of cheat, but make this positive, make this negative, and we'll put our field lines. It's not a really good color, is it? Neither is that. How about this? There we go. That we can see. And you have this kind of pattern here, right? All dictated, and if you think about it, no matter, oops, we draw it the right way. There we go. All dictated by what a positive test charge would experience if placed in the field. Okay, any questions about that? Sweet. All right, let's talk about how we measure the force field. So I'm going to use gravity as an example again, just because we've sort of covered it, and I think it's a nice lead-in. So here's our sphere, our large mass. Here are our field lines aiming inward. How do we quantify the strength of a gravitational field? What will we do in order to find out how much strength this field has? What do you think? How do we do that? So we quantify a field, right, based on the amount of force that some mass feels, okay? We have a very convenient unit of mass that we like to use, and it's called the kilogram, okay? So we can quantify a field by how many newtons of force every kilogram feels in that field, okay? So Earth's gravitational field provides how many newtons per kilogram at the surface? How many newtons does every kilogram get at the surface of Earth? We'd write this, wouldn't we? Weight equals mg, right? So how many newtons does each kilogram get? Right, 9.8. So the surface of Earth, every kilogram gets 9.8 newtons, right? If I had 2 kilograms, I get twice this, almost 20 newtons, and so on, right? Now, what else does this number play out as? Where have we seen this number before? Right, it's acceleration. Well, it turns out that a newton per kilogram, if we break it up, excuse me, we know that a newton is kilogram meter per second squared times kilograms. So what's going to happen is those will go away. And G can be expressed either in terms of newtons per kilogram as a gravitational field strength, or as the acceleration that any mass will experience, any small mass will experience in Earth's gravitational field. Okay, so the unit of measure of that is the newton per kilogram. Does that make sense? And it's different in every gravitational field. In fact, it's different depending where you go in Earth's gravitational field. As you move away, this value will decrease, right? If you get farther away, the field gets weaker, and you get less newtons per kilogram. This is an important concept to understand because it mirrors itself when we're talking about electric fields. And we don't do a lot with magnetic fields, at least in this course, but the same concept with magnetic field. How many newtons per, what do we feel in that field? So let's just define this. Okay, so let's say we have a positive charge sitting there, and we have our field lines coming out of it. Okay, and so in gravity, the main unit that we deal with when we're talking about gravity, that's the unit of mass. That's kilograms. Gravity is based on kilograms, right? We learned this back, a little while ago. Fg equals g mm over r squared, right? Units that are important are the unit of mass. Now we're talking about electric fields, and we're saying we place a positive test charge here. So if it was newtons per kilogram there, how are we going to define the strength of this field around a large charge? How are we going to do it, do you think? Exactly right. Okay, the strength of an electric field, large E, is force per unit charge, right? The amount of force this charge would feel, okay? If it's 1 Coulomb, right, and it's 1 Newton of force, then we have a 1 Newton per Coulomb field strength. Does that make sense? Now this is like, you have to measure this directly. There's mathematical ways to figure out what it would be if we know the charge here. But really, we're just saying anywhere around here, okay, we're going to have different field strengths. There should be, right, a ring around this thing. If this is spherical, a ring around this thing where the field is exactly the same strength anywhere, right? Does that make sense? Okay, and again, another sphere where anything on that, essentially, I guess that shell would have the same field strength. This concept of 3D space is going to be important in just a minute here, right? So just imagine, right, that this is in all directions, kind of like a porcupine, like spreading outward into space, and there's shells, and everywhere on that shell has the exact same field strength. Okay, these concepts become important because we have to think about, well, what would happen if I wanted to move this charge from this shell to this shell? I shouldn't say shell because we're going to get confused with electron shells, but if we move it inward, well, we have to do work. What does that tell you? If we did work, then it has potential if it's closer. Okay, so that's where we're heading with this. Before we do, we got to get all these electrostatics basics put in place. So there it is. So what units would we be talking about? This is measured in newtons. This is measured in coulombs. So E is measured then in newtons per coulomb, just as was suggested. Okay, so moving on. I mean, there's not a whole heck of a lot that we would need to do with this particular point. So this is kind of our definition of a field, and it's just, a vector arrow saying which way the field points, always based on the positive test charge. So, if they say there's a field to the right, and you are to the right, then you got to be talking about a positive test charge, right? If there's a field to the right, but you're to the left, then you're talking about a negative central charge. So you just got to, understand the, I guess what's the word, the conventions that are used when we're talking about this stuff. Moving along, we're going to get into what's called Coulombs Law now. Coulombs Law. So Coulombs Law is going to look a little bit familiar to you. It looks like this. Okay? So what this is a quantification of the amount of force two charges placed r apart will experience depending on the size of the charge. It should look familiar because it's essentially right, correct. So it's gravitational, but instead of masses, we're talking about coulombs. Instead of the gravitational constant, we have Coulomb's constant. Do you think Coulomb's constant is larger or smaller than the gravitational constant? Very much larger, yes. Coulomb's constant. Oh, and by the way, just so you know, a coulomb is like a huge amount of charge. It's giant. Probably on a daily basis, we would deal with like microcoulombs and possibly millicoulombs. Okay? So like, I mean, when you charge yourself up on the carpet and shock yourself on the doorknob, you're probably transferring millicoulombs of charge. A lightning strike might be like 1.5 coulombs. Yeah. Coulomb is massive. It's a huge amount of charge. It's funny, right? Because we don't really consider a 1 amp current to be all that gigantic. However, concentrating all of that statically on an object is like an amazingly large amount of charge. That the Van de Graaff generator probably only gets about, less than a millicoulomb on it. Probably way less. Okay, so let's just investigate this a little bit. These are measured in coulombs, right? Coulombs. This is measured in terms of meters, all right? We want force at the other end. So the little challenge here is, what units does K have to be in? So one thing in there should be newtons, right? Could have newtons over there. So units of K. It's a fun little exercise. It's got to have newtons. We've got 2 negative coulombs. What do you have down here? We have a square. Well, we gotta have coulomb, like it's on the top here with coulombs. So it's got to cancel out the 2 coulombs, right? And we're dividing by meters squared. So, yeah, here we go. So that's the units for K. Okay. No. So it's a constant, right? It's a constant. Essentially, you can think of constants as like conversion factors. So you can find this by experiment, right? You can find that, Fe must be proportional to the products of Q. Okay? Fe is inversely proportional to the distance between the 2 things, right? These can be found experimentally. If you want to actually apply numbers in terms of newtons, you need a conversion factor. Okay? If we were measuring force in some other way, there's no other way that I know of, but let's say we were measuring distance in inches, right? There would be a K constant for that. It would be a different number than the one I'm going to give you, and it would have inches in here instead of meters, right? So these are what constants do. The same thing with g, right? You could do g in terms of miles if you wanted, but you'd have to figure out a different value for it, right? Does that make sense? Okay, so the actual number that you have in SI, in MKS, if you want meters, kilograms, and seconds, is 8.99, or 9.0 is often used, 8.99 times 10 to the 9 newtons meters squared, coulomb squared. Okay? It's a very large number, yes. So what that means really, if you think about it, is let's say you have 1 on the bottom here, like 1 meter, okay? You have 1 meter, and you have 2 coulombs of charge, right? You're taking this value, multiplying it by 2, and that's how many newtons you're going to have. So what's that, like 18 times 10 to the 9 newtons for 2 coulombs placed 1 meter apart, okay? That's incredibly large, right? It's a billion newtons. Or, sorry, it's 18 billion newtons, okay? So that maybe just saying the number of a coulomb is not all that impressive, but when you think that you would have 2 charged objects of 1 coulomb, they'd either be repelling or attracting at 18 billion coulombs, okay? So let's look at a fun little example here. Let's say we want to use this, okay? We have a positive, we have a negative. Let's put them 2 meters apart, just for fun. Why not? Let's say there's 3, microcoulombs on here. Let's say there's 5 microcoulombs on here. And I say find the force of repulsion. So if you like tie these together and put a spring scale in here or something like that, what value would the spring scale read? Right, it's pulling them apart. Oh yeah, sorry, let's make them repulse. There. Okay, so now it's just a matter of electric repulsive force. It's KQQ, so K 8.99 newtons squared coulomb. We got 3 times 10 to the negative, we said micro, right? Negative 6 coulombs. 5 times 10 to the negative 6 coulombs. Oh, one thing to note, don't put negatives and positives in here, okay? It doesn't matter. You know from the picture whether it's repulsive or attractive, right? Because we have 3 situations, right? We could have repulsion from negatives. It doesn't make sense to try to put them in. Positive and negative are like one or the other. There's kind of like 3 ways this could go. So just realize that after you're going to draw which direction that happens, and it doesn't really matter. The math works the same if this were negative. There's no difference in the numbers. It's just that the force is in the opposite direction. And we've got 2 meters, so 2 meters squared. And let's do some math. Sorry, I just missed something. Times 10 to the 9. Don't forget that. So I get roughly here about 3.4 times 10 to the negative 2 newtons. It's not really very much. Maybe these charges are a little bit small. I mean, you can rub a balloon on your head and get it to stick to the wall. So I mean, there's a bit of force there. It's measurable. I don't even know if this amount of force is actually going to be measurable by anything that we have. Divide by 10 to get it in terms of grams, so pretty small. Milligrams of force, roughly. That might be enough to hold a balloon to the wall, maybe not. I don't know. Okay, anyway, so that's how you would use this. And let's just wrap her right there.